Hello everyone, my name is Juan Freire, and in this opportunity I will present our research, a Markov decision process for routing in space delayed cellular networking with uncertain contact plans. And this research is done in cooperation with the National University of Córdoba and the Exact Science faculty and the Astronomy, Mathematics and Computing faculty, also part of the National University of Córdoba. So, the electronic networking architecture has been proposed to cope with challenged networks such as those in space and in deep space systems. This type of networks are actually dominated by communications links with very high delay because of the propagation at the light speed and the very high distances involved, and also because of the disruptions of the nodes of a network where satellites can suddenly become occluded by planets, or basically because they become out of range easily from each other in the case of near Earth environments. These channels are somehow very prominent to high data loss rate because of channel error rate. The power is very limited in space, and the reception of signal and the signals can be received with a very weak power in the receiver. Also, channels into play here are highly asymmetric, and meaning that typically these networks are highly focused in downloading data to ground and not so much uploading data, which are typically only commands. So asymmetric channels are the rule and not the exception in this type of architecture. And there is a bundled protocol specification that actually is designed to cope with all these properties in DTN. What's interesting on DTN when applied to space is that the forthcoming episode of communications, also known as contacts, as well as their properties, can be determined in advance based in the orbital dynamics of the system. So to have a good idea of what this context looks like, in this picture we can see deep space assets that can communicate some information to satellite here on time 1, and this satellite can carry this data until meeting another satellite here on time 2, and eventually this satellite can deliver this data to the ground station on time 3. In this scenario, we are assuming unbounded latency because of this space proof might take several minutes to transmit this data, and then we also have episodes of connectivity, meaning that this contact has a start time and an end time of period. So the way of coping and dealing with this type of network is reducing the feedback messages. This is what bundle protocol does, and store and forward is enabled as a mean of data flow in this type of networks. As a result, data flow in a stored carry-on fashion in a network where contacts are predictable, because we can say with very good idea, very high accuracy, when a contact will happen between objects that are in space, which have an scheduled and a predictable trajectory in space. And this very property has actually motivated all the spirit in routing in the electrolytic networking. This is basically because of the concept of the contact plan. So the typical flow for operating and routing this network is, first we have a planning stage here on ground where orbital propagators and mathematical models of orbital dynamics are used in combination with communication models with basically antenna pointings, antenna gains, disappointings, and all the characteristics of the channel that are into play. We can mix them together and get what is called a contact plan, which is basically a list of all the contacts that are going to come into the future, or are going to be the future topology of the network. And with this contact, we basically feed a routing algorithm or a routing mechanism that is able to derive a route, a list of routes between one node to another, and these routes eventually can be used by the nodes themselves to forward data in this store, carry, and forward fashion. Routes can either be calculated on a central node on ground, or can either be calculated in space on the nodes themselves. The way of executing this routing varies from application to application. One of the most popular solutions is using contact graph routing, where basically this solution creates an abstraction which is called contact graph, and it's shown here on the left part of the slide, which is a not so intuitive structure representing the topology of the network. So we can see the contact plan here on the right. We had several contacts, and it's sometimes not so clear how this contact graph represents the real topology, but still the idea is each one of the nodes of this contact graph actually represents a contact in the contact plan. And what's appealing from this model is that this is a static representation of a dynamic topology. It's a network that is continually changing, and therefore is highly convenient for calculating routes. And the method is known as contact graph routing, and is what's considered in this research work. So contact graph routing can take these contact plan structures and calculate routes quite conveniently in a highly accurate fashion. However, these assumptions are highly and overly optimistic. And why I'm saying this? Because real satellite implementations actually will have to face scheduling uncertainties. These models, orbital propagators, can be highly accurate, but still we can face scheduling uncertainties in some aspects which can make the contact plan inaccurate, and basically the real topology might actually differ from the one that we are actually embracing or visualizing in our contact plan. And this can be because of the different reasons. We are talking probably about faults in the node, transient or permanent faults. We're talking about potential resets here. Remember, space is a very harsh environment. We have radiation. Temperature cycles are very stressful, and transient resets of onboard computers can happen, and this might imply that a contact that was scheduled to happen is actually not happening. So basically the topology differs from the one that is imprinted in the contact plan. Power outages might happen, batteries might drain, and satellites might go into safe mode. Also, antenna pointing or attitude inaccuracies can be quite dramatic, because one contact can happen because a satellite is pointing to another satellite or is pointing to the ground station, and this actually relates to the attitude control system, which has to meet a given constraint of attitude pointing, which if not met, the contact might just not realize as expected. We are talking about possible unexpected interferences that basically runs a contact invalid or impossible to sustain, or even last-minute mission commands that can modify the topology that have already been provisioned to nodes in the network. So this type of uncertainties needs to be considered before ever implementing a contact graph routing, scheduling, routings or calculation. Some previous work about this I would like to highlight is opportunistic CGR. CGR already focused in the occurrences of uncertainties, but they are different from what we are stating here, in the sense that opportunistic CGR basically tackles the problem of dealing with contacts that are happening that were not expected to happen. And these are more basically, I have my schedule, which is quite accurate, and then if a new contact happens, I'm able to model this contact and embrace that contact and add that to my contact plan and calculate routes considering this contact and some learning features I can have from this contact in the future. We are working in a different aspect. We're saying that the contacts that I expect to see have uncertain an uncertain feature towards the future, as we're going to discuss in the next slide. So what does uncertainty mean for us? So uncertainty means two things. Either a contact between two nodes, so for instance in this case node A to B or B to D, are not happening in any given time period because a node fails. So in this case it will be node B. If node B fails, there are basically three contacts that are going to be affected by this. And therefore these contacts indeed, after all, affect two routes. One of these routes will be completely invalidated and the other route will be, let's say in this example, it's going to be halved the capacity or the volume of that this route can actually deliver to the other node. And this is one phenomena that can happen. And the other phenomena that can happen, and we are unfortunately not considering this yet in the model we're going to present next, is the phenomena that the initial time and the end time of a contact are not so deterministic. This can be moved in time. I mean, this start time and end time are not really static and a fixed number in terms of time, but is maybe a probabilistic distribution based on how accurate our estimation is. And so this basically renders our contact plan more kind of a guessing of what's going to happen in the future than what's really expected to happen. And this is the main objective or the main problem that we're trying to deal with in this work. So we have made the first steps in this in studying how can the electoral networking deal with uncertain contact plans. In this very first model, we are going to consider only failure of the contact plan. This is that contacts that were expected to happen, they just do not happen. And we can see this here in this very simple case where we have three nodes and three different moments of this network. Node 0 see node 1 here in the first time, then 1 C2, and then 0 C2 at the end. And we can see here how the fault or the elimination of a contact that has a probability of failure, in this case of 0.5 as an example, fails. And the consequences are as follows. If node 0 wanted to transmit data to node 2, which is the ground station here, obviously the shortest path or the quickest path to get to the destination is through node 1 and then node 1 to node 2. If node 0 sends this data to node 1 and node 1 is not able to deliver this data to node 2 at the second state, then a better decision would have been to send this data directly to node 2 later, but in a safer way to get to the destination. So how do we actually model this type of things? How do we actually get some properties and study the phenomena? We do this via Markov decision process. MDPs are very appealing for this type of cases because they model both probabilistic and non-deterministic behavior. So non-determinism in our case has basically a model in what do we do with the bundle at any given moment. Shall we forward this bundle to node A, forward to node B, or shall we either keep this bundle with us because I should not forward this bundle this very moment. This has to do with the routing decision that we take for a given bundle. This is basically a decision that is best for the worst case. Basically, we want to know which is the decision that we need to take at any given moment. And then we also need to model probabilistic behaviors. And this is basically what we want to model here is that contacts that will fail with a probability of A and contacts that happens basically with a 1 minus the probability of this contact of PA in this case. So we need to model these two phenomena in a single model, and this can be achievable by this Markov decision process models as follows. So just some quick highlights. So an MDP is formally defined as a tuple where we have a countable set of states with an initial distribution and we have a finite set of actions that the system can execute, and these actions basically has a transition probabilistic function such that all these states can move from one state to the other via these actions with a given probability. And we also have these typical MTP models are described also by a set of atomic proposition and labeling. What's interesting is that non-determinism in MTP are resolved, and this resolution is expressed in a policy, which is basically a finite set of sequence of states that basically yields which action should we take next at any given moment. This type of MTP can actually be modeled and studied by what's called probabilistic computation tree logic, PCTL. We can actually feed this into model checkers in order to verify their properties and get some insight of these models. PRISM is one of these model checkers that has been specifically designed to work with MTPs. The models for PRISM are expressed in PRISM language, and we basically implemented these models for the electoral networking in PRISM. And the way of doing this is basically one model per bundle was created here. We can see here how its model is expressed. Our variables are, for instance, the number of nodes, the number of time samples. TS is time samples. TS stands for how many states do we have in our topology. In this example we just seen in the beginning, we were talking about 3 different states, 3 different moments of the topology. Each moment is described by a single static graph, to say it somehow. And then we have different actions that the module can execute. And as we can see, this is exactly the model for the example of the beginning. We have like 3 options at any given moment. So we can, which is basically the contact plan, right? So node 0 can send data to node 1 at any given moment. These are called the guards on the left part of the model. Node 1 can send to 2, or node 0 can send to 2 at these different time samples, and these decisions actually has a consequence, which are actually the updates. This is how are the variables going to be updated in this model, and this update has a probability of happening, right? So this probability is basically when I hit this action, I can either have a 0.5 possibility of going to just to the next step and not doing anything, or 1 minus 0.5 probability of changing the node of this bundle. We would mean that this bundle was effectively transmitted to another node. And we can see here on the last part that there is a next action, which basically means I just go on and step onto the next step, and which would mean that I do not transmit this bundle to anyone, and I do not attempt to transmit it to anyone. This will be all the possible actions that our model is doing in the PRISM code we are seeing here. So the transition matrix that we get out of the very simple example we have just seen is this one here on the right. And this transition matrix basically express as all the possible state that this bundle can have in this possible example, and these states are expressed by the node where the bundle is sitting and the time sample that we are expressing at any given moment. We need, in this example, we have 10 possible states, and then out of this all these possible states that are related by actions and probabilities that of these actions happening, as we see here on the right, and we can use the type of structure to check properties. So which is the maximum probability that the bundle sent from node 0 to 0 is delivered to node 2 in this case, and we can get this type of answer for this type of models and tools. In this case, PRISM says that the result is 0.8, and this is the workflow that has the maximum probability of this bundle to get into the destination, which will be, as we say, node 0, then node 0, and then node 2, and then node 2. This basically means that the higher delivery probability for this bundle will be from node 0 to directly transmit this bundle to node 2. So in order to analyze this model, we generate random scenarios and random topologies with different time step, different contact density, and uniform value failure probability for all the contacts. We are using 8 nodes network and all-to-all traffic patterns. So we're having a complex traffic pattern here. We're not considering congestion. So this is something maybe I will highlight toward the end of the presentation. And we are using the DTNs simulator. We have created in Omnet++ some time ago. It's free and open for use. It's open source code. And the routing schemes we're going to compare proof, which is basically this MTP-based routing decision where we have discussed. And we're going to compare CGR configured with the best delivery time metric, which is the default version of CGR in ION, and a different version of CGR which is honoring hop metrics. We also showing the results of CGR 2 copies, which is a version of CGR we were playing with some time that basically says send 1 copy of the bundle via the best delivery time metric and 1 bundle via the least hop count to the destination metric, and also the CGR fault aware, which is a cheat that we're doing, which is basically when a fault actually happens, the CGR can basically be aware of these faults and taking the best and the optimal decision. So we expect this to be like a theoretical unreferenced value of what is the best delivery that we can actually get in an uncertain contact plan. And these are the results. So on the left we have the delivery ratio. We're going to see that first. So obviously the CGR fault aware has the best delivery ratio. This is just like running CGR over a perfectly scheduled contact plan, and this is as good as it gets. Then we have the best next behavior is on CGR 2 copies. The CGR 2 copies sends 2 copies of the bundle, one through the quickest route and one through the most reliable route, typically because it's the less number of hops here in this case. So there are actually 2 copies flowing of the bundle. Here is the next best routing solution, but the proof model, which is the MTP model we are proposing, is the best routing solution that you can get with a single copy and without knowing which contacts are going to fail, just only using the probabilities in your favor. And then on blue we see the results of the CGR, traditional CGR with the delivery time metrics, and then we have the CGR hop as less performant option. But we see also in the energy efficiency that the CGR hops is the most efficient in terms of energy, because we honor the least number of hops to get to the destination. We're not honoring the best delivery time, so it's highly efficient in terms of energy. And then we have all the other options here. So we see that well, obviously CGR fault aware is good in terms of energy, as there is no retransmission basically in this case. And then we see that proof and the MTP model is actually quite good in terms of energy efficiency, which is basically how much transmission I am doing in order to get to the destination of this in these scenarios. CGR delivery time is the next in terms of energy efficiency, and the 2 copies is obviously is one of the most inefficient one, as 2 transmissions are actually used for every single bundle to get to the destination. We made some scalability assessments, because obviously these MTP models becomes quite large. As we can see, only a very simple network we get to 10 states, so the exponential the number of states grows exponentially. This is very limiting, and this is a quick study of how much time of processing do we need to solve this MTP in PRISM for different probability and contact density. We can see that this scales quite badly, even though we are using a 10 and 8 node network with only 10 timestamps. And the same happens with the memory use to have this model synthesized in PRISM. So we have introduced for the first time the uncertain contact plans as a way of dealing with DTNs. We use Markov decision problem as a mean to model this, and the result validated that this is the theoretical upper bound reference for single copies routing in DTN. This is a research line itself, and in the future we need to model congestion and channel errors as other factors to consider in this type of model. Scalability considerations might be improved by using heuristics or other way of solving this type of model. And most importantly, which something, in my opinion, which is the way we are working now, will be a very important advance in this, is how do we model multiple copies routing solutions for this type of uncertain contact plans. So this is what we're doing now. Unfortunately, Markov decision problems are not the way to model this, because the Markov decision problem assumes that every state you know the complete state of the network, which is unfortunately not true. In DTN, nodes will not be able to know what is the status of the packet in other nodes in a DTN, which is this cannot be modeled by MDP. We need sometimes of alternative models we are already working on, and this is sort of what future research and current effort happening at this very moment. So with this, I complete my presentation, and well, I am open for questions, and I appreciate your time in listening to me.